Hello and welcome to this lecture. Today we will take up a few problems in one-dimensional diffusion as well as reaction later on. And these are problems that you would have encountered previously, I'm quite sure, and they're rather simple and amenable to analytical solutions in most cases. However, today we shall approach these problems using the methods of scaling that we've covered in the previous lecture. And we shall see how scaling allows us to make predictions about the nature of the solution even without solving the equations, and more importantly, predictions that would hold even if the geometries are not so simple or the situations are not so simple that they would allow for analytical solution. Meaning that even in more complex scenarios where one might have to go for a numerical simulation, you should still know quite a bit about the solution and what to expect, how to choose, for example, your domain or your grid size, or in the case of an experiment, how long to take measurements, at what distance to place probes to measure concentration or temperature and so on, just by scaling the equations. So that's our goal for today's lecture. Now, before I begin to consider the first problem, let me, by way of motivation, ask you to consider a few scenarios. So first off, think about a thermometer. So the idea behind a thermometer, right, is that you have mercury inside a glass tube and you bring this tube basically in contact with your body. And the idea is you want the mercury to sense the same temperature as your body, which means you have to wait for some time before the heat of your body is transmitted through the tube into the mercury, and then it's able to expand, right? So in a thermometer, we wait. So the idea of a thermometer is you have to give it enough time so that there is no longer a temperature gradient within the glass tube. Only then can we assume that the temperature of our body and the temperature of the mercury within the glass tube is the same, right? So we have typically a wait time for uniform temperature in the tube. So the question is, what is this wait time? Now we know from practical experience that it's on the order of minutes, but can we predict this from the associated equations, or can we estimate what this time scale is? So here this is the time scale that it takes for the temperature to become uniform in a relatively thin object, a relatively thin slab. In this case, this is the glass tube. Another similar situation to this is the prototypical case of a heat transfer fin, where we typically neglect the heat transport in the smallest dimension of the film, claiming that it would be uniform much faster than it takes for heat to be transferred in the other directions, right? So heat transfer fin, right? So for example, you would have a wall, so typically you might have, in a heat exchanger scenario, a wall and there is some fluid flowing here, and you want to increase the transport of temperature to the air, and so you'd include a fin, right? Now typically we would be interested in to model the temperature of this film only in the z direction, where z is the upward direction, and if y is the cross fin direction, we typically neglect variations in y, right? And the argument usually is that y is so small, the distance in the depth of the fin is so small that the temperature T basically becomes uniform almost instantaneously by conduction. But now again you can ask this question, how small is small, and what do we mean by instantaneous, and in comparison to what other time scale? So all of these issues can be addressed by scaling, which we will do in the following problem. Okay, but the point is now that these two scenarios that I have given you, this idea of a thermometer or the fin, these correspond to situations where you have a relatively thin slab across which you have diffusion of either heat or a scalar concentrations of a species. So let's first draw that before we proceed. So today's lecture we're talking about diffusion, unsteady, right, in one dimension. At least this is what we'll start with, and these two scenarios lend themselves to be considered cause us to consider the following simplified prototypical problem. So consider a slab, right? And this is, let's say, for us now the x direction across the slab, and we neglect variations along the slab or transfers to the slab because we say the temperature there is uniform, not because of conduction, but because the boundary conditions are such that the temperature diffuses uniformly, and there's only variations in the x direction. So now on one wall, which corresponds to x equal to 0, we say the concentration is equal to C naught. Instead of temperature, let's work with concentration, because later I would want to introduce a reaction. And this is also a good example to think of when we think about diffusion into a catalyst slab or pellet, for example. Okay, so it's C naught at one end, and at the other end, which is where the depth here of the slab is capital H, yes, at the other end, x equal to h, let's say we have a no flux boundary. So now what this means, and if we start at t equal to 0 where the concentration is 0, then the fact that the concentration is maintained C naught at one wall means we'll be supplying material from one side that will ultimately reach the other wall after some time which we want to estimate, and then eventually it will keep building up until the concentration becomes uniform. So the question is, what is the time that it would take for the temperature to attain or the concentration to attain a uniform profile? That is what we are interested in both these scenarios. Okay, but there is also another scenario, a kind of flipped version of this problem, where we say that the depth of this slab is so deep that we don't really expect the concentration to ever reach all the way through and try to attain a uniform temperature. Instead, what we are interested in is to know that after a specified time, it could be a measurement time, an observation time, or a time for which we are able to supply the species, we want to know at a given time to what depth can the concentration diffuse into the slab, even though we know that it's never really going to reach all the way through. So this is the kind of scenario where we say that instead of the slab being thin, rather the slab is so deep that we can basically neglect the presence of the other boundary, and it's as if it's diffusing into an infinite domain. And then we just want to know how the penetration depth will change with time. So a classic example of this is heating of soil below the ground. Yeah, so for example, you could have the ground Yes. Yeah, so we have the ground here. Right, this is the ground, and you have soil beneath the surface of the earth. On top you might have some trees and so on, and there is heating from the sun. So let's say we know the temperature at the surface here is Tg, temperature at the ground. And what we are interested in is knowing how the soil gets heated by heating from the surface. And so we expect it to be hottest equal to Tg at the ground, and then for the temperature to kind of decrease with depth, right, as it goes into cooler soil. And we know that for all practical purposes, the depth of the ground is infinite, as we are never really going to reach that deep. In fact, well before it can reach any sufficient depth, the sun, basically we have only a finite amount of time for the sun to be present before it sets, right, and we have night. So here our timescale of interest is typically on the order of a few hours, the daylight time that we have, maybe 8 hours or so, and we want to know in that amount of time to what depth can this temperature penetrate the soil. And that will change from season to season, so the depth to which you will have relatively warm soil will keep changing. So in this type of problem, where the slab is basically practically infinite, we are more interested in the length scale, LC, to which the temperature can penetrate, and we want to know how this varies with time. So I'll call it time of observation or time of measurement, right, or time for which we have the forcing of temperature. So let's just call it T observation to denote that in general. Okay, so this is a different scenario now, where we have an infinitely deep slab and our question is fundamentally different, And then you have the case where you encounter thin slabs, and there you expect a uniform temperature, but you want to know how long you should wait for that to be attained. All right, so with these in mind, let's first begin with the case where we have a finite depth slab, where the depth is h, right? And we can now look at the unsteady state governing equation for conservation of mass here. So that we know in 1D, if you simplify things, it's just dou c by dou t. There is no flow or convection in this problem. You have the diffusion coefficient times dou square c by dou x squared. So this is our governing equation, and it has to be accompanied by one condition for in time. So c at t equal to 0 and at all positions within the slab, we start with 0 initial concentration. Now the concentration at any time but at x equal to 0, I said, is c naught at one wall, and at the other end we say that the flux of material is 0. Okay, so this is our equation and the associated boundary conditions. So now we do what we've always done, which now become routine, is to scale the equations with order 1 scaling, of course. So what this means, in order to scale it, we need to identify a characteristic scale for the x direction, or a length scale. Similarly, we need a time scale and we need a concentration scale. Now, because we want order 1 scaling, some of the scales are obvious from the equations. So for the concentration to be bounded between 0 and 1, we should choose the characteristic concentration scale as c naught. Similarly, for x, we should choose it to be the depth of the slab. So that leaves us with what the characteristic time scale should be for scaling the equations. So we leave this unknown for the moment and try to determine it from balancing the terms in our equation once we non-dimensionalize. Okay, so let's proceed with that. So we have dou c tilde by dou t tilde, where the tildes denote non-dimensional variables, and c will throw out a characteristic scale here, and so will time. This, on the other hand, will be balanced by diffusion, where we get a time scale here and then we get the length scale h squared, and of course there's a diffusivity constant in front of it. And our boundary conditions non-dimensionalize in a simple way as follows. All time at the x equal to 0 is 1, because we scaled with c naught, and the gradient at the other end is 0. Okay, that looks good. So our boundary conditions are scaled, but now the equations we are still left to determine Tc. So let's first let's choose which term should have 1. So clearly diffusion, no matter what, is going to be dominant, especially because at the end we expect the solution to reach a steady state, in which case this time dependence will become small. So let's keep diffusion as a dominant term and take multiply throughout by h square by dc naught. So what will that give us? We will get h square, the c naughts will cancel. Equation being linear, we don't have a surviving concentration scale dependence in the non-dimensionalization. So we get a group here involving the time scale, and this is a time dependent term, non-dimensional, now scaled between 0 and 1, of course, and this is the corresponding diffusion term. Okay, so now we are in a position to make some comments about times. So you see that because this is a non-dimensional group, it's clear that h square by d must be some time scale, right? So let's call that the diffusion time scale, h square over d. Remember, the dimensions of diffusivity are meter square per second, and h square is meter square, so you can see that this has the units of time. So this is the diffusion time scale. It is basically the time it takes for the material to diffuse across a slab of depth h. So in some sense this already answers our original question, which was what is the typical time we need to wait for material to diffuse across the slab and to reach a uniform concentration. So this tells us already that it should take roughly a time of the diffusion time, which is h square by d. However, is there a more formal way to see this? That is useful in more complex problems where it's not immediately obvious what we're looking for. So one formal way to do this is to say, okay, this is one intrinsic physical time scale, which we call TD. But what we are interested in is in knowing, is in representing this non-dimensional group as a ratio of this intrinsic physical time scale to the time scale at which we are observing the system. So what do I mean by that? Consider the thermometer case. So I have the thermometer, I put it in contact with a human body, and then after a certain time, let's say 5 minutes, I look at the thermometer. So in that case, the time scale of my observation or measurement, or my external time scale that I am setting with which to take readings, for example, from the thermometer, is a separate time scale from the internal system's time scale. And in this case of a thermometer, if my imposed measured time scale is much larger than the system's intrinsic time scale, I can believe that things have reached steady state. So with that in mind, other than this, we say that there is a time scale of observation, right, which is determined by me or by the experimental protocol I am using. So if I choose now my characteristic time scale to be the time scale of observation, right, so this is something set by the experiment, it's external to the system. Okay, it's just a way for us to think about questions like transience and how long it takes to reach a steady state in terms of scaling. Okay, so I choose my characteristic scale to be T observation, and then if I substitute that here, you will see I'll get a non-dimensional group. Right, times dc tilde by dt tilde. Okay, so this is the governing equation, and now that leads me to the following condition, that if h square by t observation d is much less than 1, I can then say that I have hit steady state. Why? Because if h square by t observation d is much smaller than 1, I can basically drop off this unsteady term, because dc by dt, remember, is maximum of order 1. So if this is multiplied by a very small number, this is like 0, and the equation that survives is dou square c tilde by dou x square equal to 0. And you can easily confirm that for such an equation with the given boundary conditions, the only solution possible is c equal to 1 everywhere. Right, so this is the condition for steady state, or for saying that c is equal to 1 uniformly, or the uniform profile. But this just means that the time of observation, right, must be greater than h square by d, which is basically the diffusion time. So this is the condition that we're after. It's the estimate that we have, that if the time at which we're observing the system is greater than h square by d, we can expect the concentration to be uniform. Or in other words, h square by d is the minimum time we should wait before we get a uniform temperature. So now if this time scale is small enough compared to the time scale of observation, or some other time scale in the system, so for example, if we go to our motivating problem of the fin, if I know that the time scale of diffusion in the z direction is much greater than h square by d, where h is the depth of the film, then I can assume the temperature is uniform in y. So that is what this t observation is supposed to mean. It's either the external time scale at which I measure something, or it's some other time scale that I could introduce if the problem has some additional degree of complication. But it's a way for us to introduce a non-dimensional parameter and then reach conclusions based on its value going to a small number. Okay, so that's the end of this part. Now let's consider a situation. Of course, there is this, let's move to the next stage where this need not be small, right? So let's say that h square by, if h square by t, if t observation d is order 1, or in other words, I could also say that I'm interested in problems where the observation time is equal to the diffusion time. or it's like saying that I scale my system with the t diffusion time. So this means that I'm interested in processes on time scales where the concentration profile is still developing and before it reaches its uniform state, right? So I am interested in observing the system in the unsteady regime. Then it makes sense, that's like saying t observation is td, or it's like scaling the time with the diffusion time scale, h square by d diffusivity. Right, so if I do that, my equation would then simplify to dc tilde by dt is dou square c tilde by dou x tilde square. And I would have to solve this with the given boundary conditions to obtain how concentration varies with time in the slab. I will do this in a moment. I'll show you some numerical simulations to show you how the concentration profile develops. And such unsteady problems are of course numerous in engineering and nature, where it is important for us to understand how the profile is developing because we don't want to wait for it to reach uniform. So one example of this of course is in cooking. So let's say you're cooking a patty or a cutlet, right, a vegetable cutlet. So typically you would have your cutlet base or mix, right, and you would make it in the form of a thin slab and place it upon the frying pan. Right, so this is the surface of the frying pan, which is at some hot temperature, right, because you have flames below it. Right, and the idea is now that it's basically a slab that's kept in contact with a hot surface for some time and the heat is being transferred into the slab. But the crucial thing in cooking is you don't want to overcook the food, right? So what you want to do is you want to keep this patty in contact with the frying pan long enough so that the temperature in the depth reaches typically beyond 60 degrees or so that everything cooks. But you don't want the entire slab to reach the same temperature as the bottom frying pan, which is well above 100 degrees, in which cases that if the entire patty goes above 100 degrees, you're basically burnt. Right, so you want an unsteady heat transport to happen and you want to wait just long enough for the temperature in the core of the slab to rise beyond a certain value. So this is the classic problem of yet when this happens, it's not like the patty is infinitely deep. Even as the core reaches a certain temperature, the free surface will start to heat up. And then typically what you would do is, instead of waiting to be unidirectional, you would flip the cutlet and fry it on the other side. So this is a fundamentally unsteady heat transfer problem, and here it makes sense to scale your time scale with the t diffusion and you get the appropriate scaled equation. And so typically the flipping time that you would want to maintain would be maybe some fraction of the diffusion time, certainly not larger than the diffusion time, because that your stuff would already get burnt by then. So this is an example of where we would be interested in solving the unsteady problem. But even here you know that scaling helps because it kind of gives you a rough estimate of when you need to flip the patty that you're trying to fry. And that of course depends on the diffusivity of the patty, the thickness of the patty. So you know the time scale from here already goes as h squared by d. So typically this means this is why we don't try to make very thick cutlets, right? At the same time we don't want to make very thin cutlets, so they will burn almost immediately. So that's basically a competition that lets you decide how thick you should make your the patty or the cutlet you're trying to fry, let's say for a burger. Another thing to think about is typically if you make a patty and you make patties of two different thicknesses, one double the other, naively people think that the patty that's twice as thick will take twice the amount of time to cook. But you can see from our scaling that it will actually take 4 times the amount of time, because the time scale goes as h squared because of the nature of diffusion. So this is some simple analysis which can sometimes contradict what we think of naively in the kitchen, that if you double the thickness the time will double. Rather it's going to quadruple, and these are things that you can of course see if you do it yourself. Alright, so let's leave this now for the moment, and I'll come back to this to show you some numerical demonstrations of this and of the relevance of these scales that we've obtained, of the diffusion scale that we obtained.